welcome back to the course of applied elasticity. In the first week of lectures, we were talking about the introduction to tensor, followed by tensor algebra and tensor calculus, which were the mathematical preliminaries which are required to discuss about the theory of elasticity. Now this week onwards, we are going to enter into the actual subject of elasticity, and we are going to start with the kinematics of deformation, which will be followed by definition of various strain measures. So let us start the kinematics of deformation. Now we are going to consider deformation of a continuum. So let us consider capital X1, capital X2, capital X3 to be the coordinates in the undeformed configuration. We are considering this particular body. P is any point on the body whose position vector is defined by capital X. So components of capital X vector are x1, x2, x3 all capital. This particular configuration is defined as initial time t naught and defined by capital omega naught. This is called initial configuration or undeformed configuration. Now upon loading, when this body is subjected to various external forces along with the boundary condition, this body will deform. It will move from initial configuration to the deformed configuration as we are going from time t naught to any specific time t. So that transformation and deformation results the deformed body where point P has moved to another point P prime. Now P prime is defined by a position vector small x with coordinate small x1, small x2 and small x3. So capital X was the undeformed position vector of point P, small x is the deformed position vector of point P prime, and this deformed configuration is defined at any time t, which is also named or referred as current configuration. Now this deformation from capital X to small x is defined through a transformation mapping chi. So small x is defined as this transformation mapping chi, which is function of undeformed coordinate or position vector capital X and time t as shown in the figure. So this chi is called the deformation mapping, which is function of capital X undeformed material position vector and time t. Now capital X vector is capital Xi ei, whereas small x vector is small xi ei, ei being the unit vectors for both undeformed as well as deformed configuration. We are choosing the coinciding reference frame in both initial as well as current or deformed configuration. Now from this figure we can go for the kinematics of deformation for this continuum, and two assumptions for this theory are: the body is assumed to be continuous without any discontinuity within the domain, and it is assumed to be deformable, it is not rigid. With the loading, body is going to deform, and an infinitesimal volume element, a small volume element taken within the body, represents the behavior of the total continuum. With these assumptions, we are moving forward. Now capital X is the position vector of material point P in the initial state, where capital X1, capital X2, capital X3 are three components of the capital X vector. Now it is deformed to small x position vector through a transformation defined through chi. So chi transformation is taking capital X as input and giving small x as output, through which the deformation mapping is defined, and this deformation can be mathematically described with the help of two different approaches. The first one is called material or Lagrangian approach, or material or Lagrangian description, whereas the second one is called spatial or Eulerian description. Now in case of material or Lagrangian description, we are doing all the calculations with respect to initial or undeformed state, whereas for the case of Eulerian or spatial description, all the calculations are done with respect to the deformed or the current configuration. So, description of the material point, we are choosing any material point and we are going to describe it with respect to both the approach. The first approach is material or Lagrangian description. Now, motion of the material point within the body is traced by the undeformed material coordinates capital Xi and time t in the Lagrangian description approach. So, for any quantity phi, the phi is function of undeformed material coordinates capital X1, capital X2, capital X3 as well as time. For the case of material description, phi can be any quantity, it may be stress, may be temperature, velocity, acceleration, anything for a particular point P within the body. So, for material description, all the quantities, all the properties of the body are expressed as function of undeformed coordinates capital Xi along with time. Now, coming to the Eulerian description of motion or spatial description of motion, here the motion is traced with respect to spatial or the deformed coordinates small xi and time. So, for this case we consider a fixed point in space because we are choosing small xi as our point of interest. So, the point is fixed in space which is occupied by different material points as the time progresses. We are not tracing the motion of a particular material point in the spatial description, whereas for the Lagrangian description, as capital Xy was chosen to be fixed, for a specific material point we are choosing we are observing how it is deforming in space with time. Now, coming back to spatial description, here any quantity phi is function of small xi, small x1, small x2, small x3 and time, the deformed components of the position vector. Now, coming to the time derivative in both material and spatial descriptions. Considering the material or the Lagrangian description, phi is function of capital X vector and time. So, the total time derivative of phi d dt, where d is a capital D, refers to total time derivative. So, total time derivative of phi, which is function of capital X and time t, this is equals to del del t of phi capital X comma t with capital X being fixed. Now, capital X is defined as the position vector in undeformed or initial configuration, and this is always a fixed quantity. These are not changing with time. Thus, del capital X del t equals to 0, and for such cases the total time derivative of phi is nothing but the partial derivative of phi with respect to t. Del phi del t is the total time derivative of phi in the Lagrangian description, because phi is function of capital X and capital X does not change with time. So, partial derivative of phi with respect to t defines the total derivative of phi with respect to t. This is called material time derivative. Now, coming to spatial description or Eulerian description, here phi is function of small x and time. So, here the time derivative of phi, total time derivative of phi is d dt of phi function of small x comma t. Now, both small x as well as time, both are changing here. So, for the previous case capital X was not changing with time, but here the deformed position vector small x is continuously changing as the body is continuously deforming. So, here d phi dt is equals to summation of two set of terms. First, in this term we are taking that time derivative with respect to t, whereas here we are causing the changes coming due to changes in small xi components. So, d phi dt can be written as del phi del t plus del phi del xi into dxi dt. dxi dt, this quantity is nothing but the velocity component vi in the deformed configuration. So, this is written as vi and thus the total time derivative becomes del phi del t plus Vi del phi del xi. Vi del phi del xi can also be written as V vector dot gradient of phi vector. So, total time derivative in the spatial or Eulerian description is having two terms. One is del phi del t, which was also present for Lagrangian description. Second term is V dot grad of phi. So, this first term is called local derivative with respect to time, whereas second term is called convective derivative. So, total derivative in spatial coordinate is summation of local derivative and the convective derivative. Now, considering phi to be velocity, let us say phi we are choosing as velocity of the material and our objective is to obtain the acceleration. So, we need to take the time differentiation of phi, which is nothing but velocity vector. So, in the Lagrangian description or material description, the V is function of capital X and time. Thus, acceleration will be d dt of V, which is nothing but del V del t, the partial derivative of V with respect to time. Now, coming to the spatial or Eulerian description, where V is function of small x, the deformed coordinate and time. Here acceleration will have two terms, both local derivative as well as convective derivative. So, A vector will be del V del t plus gradient of V dot V. Now, we can further simplify this and write in initial form as AI, the ith component of acceleration vector, is equals to del Vi del t plus del Vi del xj times Vj. So, this is called the spatial time derivative or acceleration in the spatial approach. Now, moving forward to the displacement fields or definition of displacement vector. We are considering the initial configuration at time t naught, which is deformed through the transformation mapping chi to this deformed configuration where point P is moving to P prime. Now, we are choosing another point Q in undeformed configuration, which moves to another point Q prime in the deformed configuration. Now, P to Q, a small elementary length of d capital X, deforms to P prime Q prime, a small element in the deformed coordinate d small x. Now, the displacement of point P is defined as the vector P to P prime, which is u vector. Normally, we use this symbol u as the displacement component. In the material description, this is function of capital X and time. So, displacement of point P is u x comma t, displacement of point Q is u x plus d x comma t, because point Q is dx amount away from point P. The formal definition of displacement vector of particle P is in the Lagrangian or material description is u equals to small x minus capital X, where both u and small x are function of undeformed material coordinate capital X and time. This is the definition of displacement vector in material description. Now, coming to the definition in the spatial or Eulerian description, u is once again small x minus capital X, but here capital X and u both are written as function of small x. So, if we are expressing all the quantities as function of deformed coordinate small x, then that is the Eulerian description. So, u small x comma t is equals to small x vector minus capital X, which is also function of small x comma t. Now, coming to the types of rigid body motion. If the body is not elastic, if we consider the body to be rigid, then with the help of the nature of the expression for u, the displacement vector, we can define various types of rigid body motion. We are going to start with rigid body translation, where small x is equals to capital X plus some function of time. This Ct is independent of x, and at time t equals to 0, Ct must be 0, which will ensure coinciding small x with capital X at initial time t equals to 0. Displacement u will be small x minus capital X, which is Ct independent of x, only function of time, means the body is continuously translating along a straight line or along a curved path. This is called rigid body translation case. Now coming to the next type of motion, rigid body rotation. Here the relation between small x and capital X is like small x vector minus b vector is equals to q times capital X minus b, where q is an orthogonal tensor referring to the rotation, and at time t equals to 0, q0 should be I. So, time t equals to 0, q0 being I, this would result small x is equals to capital X at t equals to 0. So, they must be coinciding at time t equals to 0, and this refers to the rotation about a fixed point whose position vector is given as capital X equals to b. This is the case of rigid body rotation, and in general any 3-dimensional general rigid body motion is combination of translation and rotation. So, for such cases small x will be combination of two previous cases, that is Ct plus Qt acting over x minus b, capital X minus b. This is the case of general rigid body motion. Now, we are going to discuss few example problems. We are going to solve a few problems related to kinematics of deformation. So, let us consider motion of a body being described by this given mapping. Small x1 is capital X1 plus t square capital X2, small x2 is capital X2 plus t square capital X1, and small x3 is same as capital X3. The first part is determine the path of the particle which was originally at capital X vector equals to 1 to 1, and the velocity and acceleration components of the same particle at time t equals to 2 seconds. So, this is the problem of material description. The capital X is given, at that point you need to find out the path of the particle, its velocity and acceleration. So, this is the given transformation mapping. From this, if you are writing a capital X and small x components, they are 1 to 1, and in the deformed coordinate they are 1 plus 2 t square, 2 plus t square and 1. Now, I have simply written small x1, small x2 and small x3 as 1 plus 2 t square, 2 plus t square and x3 equals to 1. Now, we can simply combine them by removal of time t, and that will result these two equations. The first two equations x1 and x2 can be combined with the help of removal of t as x1 minus 2x2 plus 3 equals to 0, and x3 equals to 1 will remain as it is. Now, this first expression is equation of a straight line, whereas x3 equals to 1 refers to a plane which is parallel to x1 x2 plane at a constant value of x3 equals to 1. So, thus the particle is going to move on a straight line defined by this equation on the plane x3 equals to 1. This is the trace of the particle which was initially located at capital X equals to 1, 2, 1. Now, coming to the velocity and acceleration of that particle at given time t. So, for finding velocity in the material description, we just need to take the partial derivative with respect to time, because all small x1, small x2, small x3 are described as function of capital X1, capital X2, capital X3. So, this is in the material frame or Lagrangian formulation. So, taking the time derivative of all three position components, the velocity components can be obtained as v1 equals to del x1 del t equals to 2t capital X2. Similarly, v2 is 2t capital X1, v3 equals to 0, because x3 and capital X3 and small x3 were same. It is independent of time. Taking the derivative with respect to time once again, from the velocity components we can obtain the acceleration components as well. Those will be a1 is 2 capital X2, a2 is 2 capital X1, a3 is 0, and these are the velocity and acceleration in the material description. Now, putting the values of capital X1, X2, X3 to be 1, 2 and 1 respectively, and at given time t equals to 2 seconds, the velocity vector components can be obtained as 8, 4, 0 and acceleration vector components can be obtained as 4, 2, 0. This is for the velocity and position vector solved using the material description. Now coming to the second part of the problem, where we have to solve using the spatial description. So small x1, small x2, small x3 were given as functions of capital X1, capital X2, capital X3. V components and A components, velocity and acceleration components were also obtained in terms of capital Xi, the undeformed locations. Now if we want to take it back to the spatial configuration, spatial approach, then we need to invert these equations of motion and need to write capital X1, capital X2, capital X3 as functions of small x1, small x2 and small x3. So starting with these three equations of the material description, we can get these three equations of the spatial description, where capital X1 is equals to small x1 minus t square small x2 divided by 1 minus t to the power 4. Similarly, capital X2 and capital X3 can also derive. This is by simple algebraic manipulation. Now small v1, which was defined as 2t capital X2. Now x2, capital X2 is replaced with this expression, which is function of small x1 and small x2, and thus this will become v1 will be 2t times x2 small x2 minus t square small x1 divided by 1 minus t to the power 4. Similarly, v2 and v3 all can be expressed as function of small x1, small x2 and small x3. Similarly, the acceleration components, by replacing the expression of x1, capital X2 and capital X3, the acceleration components can also be written as function of spatial coordinates small x1, small x2 and small x3. Now for the given problem, in the spatial description, one small x vector is given as 1, 0, 1. Small x1 is equals to 1, small x2 is 0, small x3 is 1 at time t equals to 2 seconds. So substituting all these values, the velocity of the spatial point at time 2 seconds can be obtained as 16 by 15 minus 4 by 15 and 0. The acceleration components can be obtained as 8 by 15 minus 2 by 15 and 0. So using this approach, you can solve for velocity and acceleration in both material as well as spatial description. Now coming to the second problem, where the motion is given as small x1 is equals to e to the power minus t capital X1, small x2 is e to the power t capital X2, small x3 is e to the power minus t minus 1 times capital X2 plus x3. The temperature field of the body in the spatial description, that is theta, is given as e to the power minus t multiplied with small x1 minus 2 times small x2 plus 3 times small x3. You are asked to find out the velocity field in the spatial formulation, and then using that determine the time derivative of theta, this temperature field d theta dt. So the problem is given in the material description. The deformed coordinates small x1, small x2, small x3 are given as function of material coordinate capital X1, capital X2, capital X3. By taking the time derivative, we can get the velocity components v1, v2, v3 in the material description as minus capital X1 e to the power minus t, e to the power t capital X2 and minus of e to the power minus t capital X2. These are the velocity components in the material description. Now as we want to find out the velocity in the spatial form, we need to invert the equations of motion. So by expressing capital Xi as a function of small xi, we can get this set of expressions. This is by inverting the equation. Capital Xi can be obtained as e to the power t small x1, capital X2 is e to the power minus t small x2, capital X3 is small x3 plus e to the power minus t minus of e to the power minus 2t times small x2. and replacing these values or these expressions of capital X1, capital X2, capital X3 in the velocity field, we can express the velocity field in the special description as V1 is minus x small x1, V2 is small x2, V3 is minus small x2 e to the power minus 2t. So, for any given problem, if we want to express the field in the special description, first we need to invert the equation of motion, express small x components as function of capital X component, and then find out the respective velocity, acceleration, all the components as required. Now, coming to the temperature field. Temperature field here is given as e to the power minus t times small x1 minus 2 small x2 plus 3 small x3. We need to find out the gradient of the temperature field, which can be easily obtained as e to the power minus t times E1 minus 2 E2 plus 3 E3. Why this gradient is required? This is required because we need to take the total time derivative in special form, which involves local term as well as convective term. The convective derivative term include the gradient of the theta operator. Now, d theta dt in the special form, total derivative of temperature field theta can be written as del theta del t, the local time derivative of theta, plus v dot gradient of theta. V is the velocity field. Now, both v and gradient of theta we had obtained in the spatial configuration. So, v was minus small x1 E1 plus small x2 E2 minus small x2 e to the power minus 2t E3, which was obtained in the previous slide. Taking the dot product of this v with the obtained delta theta, the gradient of theta, this gradient of theta and this v, we are taking a dot product of that, which results these three terms, which are the convective time derivative term. Whereas, for the given expression of theta, if you take the partial time derivative, that would result del theta del t, the first set of terms which are called the local time derivative term. And if you simplify that, these 6 terms, few of them will be cancelled, and finally, the total time derivative of the temperature field d theta dt would equals to minus 2 small x1 e to the power minus t minus 3 small x2 e to the power minus 3t minus 3 small x3 e to the power minus t. This is the change in the temperature field in the spatial description, the answer which was asked in the problem. And if you were asked to obtain it in the material description, then no need to consider the convective term. This term v dot grad of phi is not required to be considered for the material description. D theta dt would just become del theta del t in the material description. So, in this lecture we had introduced the basics of deformation of a continuum using both Lagrangian and Eulerian description. We had also talked about the material and spatial